Hi everyone, it's Danielle Harris here with the lecture about multipliers and indirect methods as part of the online distance course. And over the course of this lecture we'll talk about what a multiplier is and how and why we would use them. We'll discuss what we mean by Q counting, we'll talk about indirect surveys and give examples, and also talk about lure and trapping point transect surveys. Now we can incorporate multipliers into distance sampling analyses and into program distance, as shown here. So in program distance you can, during your project setup, incorporate information about any multipliers that you're using and associated standard errors or degrees of freedom. So you can see here an example where we've ticked that we are dealing with a survey where G0 was less than 1. And you can see that distance will add the appropriate fields accordingly. So in the case where G0 is less than 1, if we didn't do anything about it, then the standard method would produce a density estimate that is proportional to the true density. However, if we know that G0 is less than 1, we can estimate the true density by incorporating G0 into our density estimator, and you can see that it's been incorporated into the denominator of the estimator as shown. And anything that we include in the density estimator to scale our density estimate is called a multiplier. And in some surveys, cues might be the object of detection rather than the animal itself. So you could think about whale blows or bird song. And in that case, for these cues, animal density is estimated by first taking the cue density and dividing by some cue rate. And in the density estimator below, you can see that the density of cues is divided by the cue rate to give us the density of animals. And that R, the Q rate, is another form of multiplier. So there are many forms of multipliers, and if we denote them generally by the letter C, we could have a multiplier that is a known constant, such as if the sampling fraction was not equal to 1. So an example might be if we have a point transect and we've not been able to survey all of the point transect, but we know that we surveyed 3/4 of the circle, then we know the sampling fraction. Or the multiplier might be a parameter or a product of parameters that is estimated. So we, as discussed, could have some estimate for G0 being less than 1. We could have an estimate of the proportion of the population being surveyed, and we'll come on to some examples of that. If it's Q counting, we'll need an estimate of the Q rate. And in other forms of indirect surveys, we need other multipliers to help us estimate the density of animals from the density of the object that was being surveyed. And dung surveys are an example of indirect surveys, and the parameter that you need is some estimate of dung production rate. So here's an example if our sampling fraction is not equal to 1. So in a one-sided line transect survey, C, the multiplier, could be denoted as 0.5 to represent the fraction of the strip surveyed. And in the density estimator, you can see that 0.5 on the denominator, and that enables us to estimate density correctly. Similarly, in the point transect sampling example, if we only surveyed 1/4 of a circle, C would be equal to 0.25 and again placed into the density estimator. Another example with points is if we visited a point 5 times and we want to reflect that increased effort. Now our multiplier is equal to 5. And there's a form of Q counting where we do use the proportion of the circle covered by an observer, but we'll come on to that later. So those were all multipliers that were known. In examples where the multiplier is a parameter to be estimated, we might have surveys where G0 is less than 1, and then we have to provide an estimate of that G0 probability. We might have surveys in which only a proportion of the population is surveyed, and so this could be related to the availability of the animals to be surveyed. So one example is desert tortoises that spend their time in burrows underground, and so we would need an estimate of the proportion of animals that are underground and unavailable to be surveyed at any one time. Seabirds spending time on land and at sea, depending on where they're being surveyed, you'd need to account for the proportion of the population that was in the other location. And another example are whales with long dive times, so that when you're doing surveys from ships, you are aware that you are only able to detect a portion of the population, and that some proportion are under the surface and unavailable to be detected. And all of those proportions are likely to be estimates. We've already talked about Q counting, where we would need a Q rate, and as I mentioned before, indirect surveys often come with parameters that need to be estimated, and we'll come on to those later. So when we have a multiplier that's a parameter to be estimated, that parameter will have an associated variance, and then we need to incorporate that variance into our overall density estimate. And so for line transect sampling, if we modify the density estimator by including C, some parameter, then we need to reflect the variance associated with that parameter in our variance estimate of the whole density estimate. And so we can use the delta method to easily incorporate the associated variance of the multiplier. And similarly for point transect sampling, again, we can incorporate the variance associated with any multipliers through the delta method. Now, we can think about Q counting with point transects, and an example of this is if you were an observer listening to birds and your Q is a burst of song, and the song is an instantaneous cue, so it can be something that you can observe even if you have birds moving around during your surveying period. So cues can be a useful way to deal with animal movement. So in a Q counting point transect survey, you go about estimating distances to the cues that you detect, just as usual. And then you would use the density estimator to first estimate Q density. Now, you'll note below that we have density of Qs here, and if we compare that to the standard point transect estimator in the bottom right hand corner, you'll note that there's no K in the density of Qs estimator. And that's because we're going to use time as part of the estimator, and here time is the total time spent at all of the points. And so here we're using time as our effort rather than the number of points. When we incorporate the number of the time into our density estimator, that allows us to estimate the number of Qs, or the density of Qs per unit area per unit time. And then the final step is to turn that density of Qs per unit area per unit time into an estimate of animal density, and in order to do that we need the Q rate, which is the estimated number of Qs per animal per unit time. And then we can take our density of Qs and divide it by the Q rate to give us the density of animals. And so in this case we have another component of variance. We have the CV associated with our density of Qs per unit time, and then we have the CV associated with the Q rate, and combined that allows us to estimate the CV of the density of animals. Now there's another form of Q counting which can be considered in relation to line transects, and this was developed for detecting whale blows rather than individual whales, because it was easier to detect a whale blow than to track the same animal and make sure that you were not double counting the same animal, for example. So in this case we need the following things. We have some ship moving forward through time and space, and we have an observer who's looking out over some fraction of a circle and detecting whale blows and measuring the distance to those blows. So the first thing we need is to acknowledge that we're only monitoring a fraction of the circle. So we can use this information to estimate the density of Qs, and this simplifies into this expression here. You'll note that we have h of 0 here. So although this is a line transect survey, we're borrowing point transect methodology, which is why you see an h of 0 here rather than f of 0. And I should say that you can refer to chapter 3 in the 2001 distance sampling book, and also chapter 9 in the 2015 book, if you want more detail and more information about any of these topics. So we can use this estimator to get the density of Qs per unit area, and again we searched over time, so we can incorporate the time element into our estimator, which gives us the number of Qs per unit area per unit time. And in distance you can set up a dedicated Q counting project, and you can actually select that that's what you're wanting to analyse. Again, if you tell distance you're interested in setting up a Q counting project, then it will be expecting that you'll have a Q rate to add to the project, and associated standard error with that Q rate. And so if you set up a Q counting project in distance, you would expect to see these different fields created in the project browser. So you can see the area space where you would put in your Q rate and Q rate standard error information. You have columns where you can specify the sampling fraction, and then you also have a column for search time during the Q count survey. So thinking a little bit more about what do we mean by an indirect survey. So this is useful when the direct distance sampling of a population is difficult, but you can estimate the density of some object produced by the animal. So it's a similar idea to thinking about the animal producing a Q, but now we're thinking about some physical object that the animal produces. And so some examples are dung surveys, which have been used for deer, elephants, big cats, and also nests, which are built by apes. Now, if you have some idea of the production rate and the disappearance rate of these objects, then you can estimate animal density from an indirect survey of those objects. But there's a key difference here that you need to be aware of. For a direct survey, when you're observing the animals, the estimate of abundance that you generate is applicable to the time that the survey was conducted. For an indirect survey, the final estimate of abundance or density is an average over the time period corresponding to the mean time for the object that you're surveying to decay. So you just have to bear in mind how you interpret the results of an indirect survey. So let's have a look at some estimators for indirect surveys. So an example here is a line transect survey using dung, but the same ideas would apply to nest surveys. So we can use our normal estimators to estimate the density of the object of interest, in this case dung density. And if we know the parameter associated with the mean time for the dung to decay, let's say in days, we can take that dung density that we've estimated, divide through by the decay time to give us this estimate G, which can be interpreted as the dung production per day per unit area. And then the last piece of the puzzle is if we know the estimated daily production of dung by one animal, then we can use another multiplier, R in this case, to adjust G to give us the density of animals that produce the dung that we observed. And you can note that both G and R, and G being a function of D, these are all estimated values and all have associated variances. So for dung surveys, you have to estimate rates of decay and production. And so just here are a few pointers if you're interested in thinking about these types of surveys further. So to estimate dung production rate, you could observe the animals in the wild in the study region and record their defecation rate. You could also observe animals in captivity, but trying to create an environment that's as close as possible to that of the study region. And there are things to discuss about whether or not you could adequately recreate wild environments in captivity. One example, though, is you could put a known number of captive animals into a natural enclosure clear of any dung. You could leave them for a period that is less than the shortest decay time. Count or estimate the number of dung piles at the end of that period, and then the defecation rate is estimated from the number of dung piles divided by the number of animals and number of days in the enclosure. So you know that none of the dung piles will have decayed because they've been left for a period that's less than the shortest decay time, and that will give you an estimate of how many dung piles each animal produced per day. Now, bearing in mind that the sample size here is the number of animals that you used in your study, not the number of dung piles. And you could think of similar considerations when you're trying to figure out a nest production rate. To estimate the rates at which dung may decay, you have to consider that these decay rates will likely vary seasonally and spatially. And so it's important to carry out the decay rate study in the region and the time leading up to the survey. And this is true for many multipliers that we discuss. In order for the multiplier to be applicable to your main survey, it has to be relevant to the animals that are occurring within your main survey. So if you have to do any auxiliary experiments in order to get these rates or these parameters, bear in mind that they need to be appropriate for the time and place of your main survey. Back to thinking about dung decay, you would want to define some consistent criteria for determining whether the dung has decayed. And then you would search and mark fresh dung piles at representative sample sites at intervals of time which span the decay period of dung. And so during a line transect survey, you would pay a single visit to each marked dung pile and record whether or not it's decayed. And you may need to conduct more visits if you have a long line transect survey. And then you can analyse those data using a logistic regression analysis with time between marking and the revisit as the explanatory variable, and you could also incorporate additional variables into your analysis as required. And so you could apply a similar idea to thinking about estimating nest decay rates. So when it comes to the analysis and setting up the analysis appropriately, there's a multiplier tab in your model definition properties window. And so you can tell distance how you want to apply the multiplier and whether it's something that should be divided by or multiplied by in your density estimator. Now, moving on to trapping and lure point translate. These are another particular type of study design. And in this case, you only have one trap or lure per sampling plot. So the question is, how do you estimate a detection function in this case? And the key thing here is we're trapping animals, so we don't know their initial location before they're trapped or lured. So we don't have distances from the point. So therefore we need to conduct an auxiliary experiment where we take a sample of animals whose initial location is known, and then we record whether each of these is trapped or lured to a given point. And here is an example with Scottish crossbills, and you can see the reference below. And so you build up a detection function using a logistic regression, and your explanatory variable is the initial distance of the animal from the lure, and then whether it was captured or not by the lure. And then you can fit a logistic regression curve to those 0 and 1 data, and this gives you a probability of, in this case, being lured to the point. And the important thing to notice here is that when you fit this model, there's no requirement for G0 to be 1. Here's another example with key Largo wood rats. And in this case, multiple animals, both males and females, were radio collared. And using many trials, these animals were exposed to traps, and sex-specific random effects models were used to estimate the detection probabilities as function of distance of animal from the trap, just as with the crossbills. And so again, you can see here with the fitted models, you've got females in the plot above and males below. Both sexes were not certain to be captured, even if they were at 0 distance from a trap. And this is important information to collect, obviously, when using these types of studies. And finally, another type of experiment to determine the detection function using this auxiliary experiment or trial approach was used with harbour porpoise in the Baltic Sea. And this was a passive acoustic study where listening devices, sea pods, were placed in the Baltic Sea. You can see in this picture below several hundred sea pods were actually placed around the Baltic. But there was no way to determine distance of detected porpoise from the sea pods just using the detections alone. So a trial had to be set up where porpoises were visually tracked by observers going past sea pods. And so a logistic regression could be performed where, knowing the distance of the animal from the sea pod using the visual observations, it could be determined whether that animal was detected or not by a given sea pod. And again, notice here that even at 0 distance from a pod, the probability of detection was only about 0.25. So these trial-based approaches to determining detection functions, one advantage is that we don't have to assume that detection at the point is certain. We're conducting an experiment and it allows us to actually estimate G0, and that G0 can be less than 1, as shown in all 3 of the previous examples. The disadvantage is it's an auxiliary trial, which may often include further assumptions. One being, is the trial applicable to the animals in our main survey? If we conduct the experiment in a particular time and place, does it apply to the animals across the whole survey area and period? And for these trials, we need to know the initial location of a number of animals, either through radio tagging or the lure trials, or as with the porpoise, using visual observations. So it can be quite a labour-intensive way to determine a detection function. And with that, that's the end of the multiplier and indirect survey lecture.